We are still in section 3.8, talking about related rates problems, and I have a couple more examples. This next example is example 48. A hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So again, first step, draw your picture. Now I'm not going to write step 1, 2, 3, 4, 5, 6, etc. anymore. I'm just going to work the problem for you, okay? And I wouldn't recommend you're writing step 1, 2, 3, etc. either. Just eventually get comfortable with working these problems. So we have a balloon. We're going to say this is the ground. The balloon took off from here and it's rising up. So this is going up. That means the height of the balloon y is changing. I'm calling that y. And then the other thing I know is changing. First of all, I know the distance from this rangefinder to where the balloon took off is 150. That's not a variable. That will stay 150. What is changing is this angle of elevation. This rangefinder is following the balloon, right? It's following the balloon as the balloon goes up. So this angle that the rangefinder is looking at the balloon is changing. So the things that are changing are theta and y. So I need to come up with a relationship between theta and y. So what I really have here is a triangle. Right? I have a triangle, so I need to use a trig function. Okay, but the bottom line is, what do I know? First of all, I know d theta dt. I'm told that it's increasing at a rate of 0.14 radians per minute, right? The angle is increasing at a rate of 0.14 radians per minute. And then I want to know how fast is the balloon rising? In other words, what's the rate of change of the height of the balloon, dy dt? How fast is the balloon rising? When that angle is exactly pi over 4. At the very moment in time it's pi over 4. It's only pi over 4 at one instant in time. So I need a relationship between y and theta. Now I know this side's 150. Okay, so I have a relationship between the side opposite of an angle and the side adjacent of an angle. Hopefully that rings true as the tangent, right? Tangent of theta would be y over 150, and I see I wrote that right here. So I have the relationship between my two variables. So then the next step is to differentiate both sides with respect to t. Let me bring this down a little bit. I'm differentiating both sides of this equation now with respect to t, time, right? Thinking of both theta and y as being unknown functions at t. So I have to use the implicit differentiation or the chain rule on both sides. So the derivative of tangent first is secant squared evaluated at the inside theta times the derivative of the inside, which is d theta dt, equals 1 over 150 is just a constant, so 1 over 150 times the derivative of y dy dt. And then I solve for dy dt by just simply multiplying both sides by 150. And I want to evaluate that at the exact moment in time when the angle itself is pi over 4. So multiplying both sides by 150 was 150 times secant squared theta d theta dt. And I want that evaluated exactly when theta is pi over 4. So hopefully theta equals pi over 4 or 45 degrees. You know the secant of that is square root of 2. So the secant squared is square root of 2 squared, or 2. So 150 times 2 is 300 times 0.14 gives me 42 feet per minute.